Hello everyone. So it's time for recitation number 13, the last recitation for this semester, where we'll be doing a revision over really the ideas that we've been learning for the final. Now, just a cool trivia, this is recitation number 13, but like the most ever recitations I've given in this course was 11. So it's cool that we not only broke the record with our 12th recitation, but we even set another one right away. So this is like the most recitations we've ever had in one semester for this course. Great. So let's just go through those ideas. So a reminder, like the last layer that we added in our hierarchy was the Turing machines, which really answers the question, what is a computer? Well, it's a Turing machine. If you break it down into its most basic format, like what's the simplest tools you can use to really make anything like Facebook, YouTube, Instagram, anything, whether it's a website or an application, it's a game. Really, if you strip it to its bare bones, you just really need these operations offered by a Turing machine to do that, which is at any point, you are either reading some piece of information from a tape and you can write over it, or you can move right or left. Stripping it down to just these simplest tools is all you need really to create anything. Now, again, it's not necessarily going to be efficient, but it is technically feasible if you have enough, like an endless tape. If you have enough memory, you could do it using a Turing machine. And so in terms of Turing machines, really the thing we want to be comfortable with is either number one, drawing a machine, giving a description for a machine, or if you're given a machine, will you be able to understand it, analyze it? So for this one, we'll be trying to give a high-level description. So we'll be describing a machine and we'll be drawing it. Now this one, I'll leave it to you to try to practice. So BN, AN, CN. We've kind of seen this idea before, right? If you, well, just like pause for a second and think how you could solve this. So the idea is, it's kind of been seen a lot in this semester and even Turing machines. So if you had something like triple A's, BB or BBB, AAA, BBB, well, what are you going to do? You'll remove this B, put an X, then you'll find an A, then you'll find a B, and you're going to go all the way back and keep doing this. You might be using different symbols or multiple symbols when you're crossing, but the idea is essentially this. And you might do something like check if your string is actually of the format B star, A star, B star before you even start crossing. So that might be a good idea. So I'll leave this to you because we've done this something similar before when we did the Turing machine for AN, BN, CN. If you think about it, it's the exact same question, but different letters, right? Both of these you can't do them in a PDA. It's not enough. You're going to need a Turing machine for them. I'll leave it to you because I'm more interested in trying to solve this problem. Now, if you're comfortable with this type of level of problems, that'll be great. And this one is just like to really see maybe something more practical in terms of Turing machines, because everything we've been doing so far is just a format of some strings, right? But here we're actually going to be doing something that you might use in your daily programming. So give a high-level description for a machine that decides the following. We have the language L, which is made up of W, hashtag W, such that W is a substring of X. Okay, so we have W, hashtag X. W is some substring of X. For example, the following. We have 110 and 110 right here. So this will be accepted because, well, if this is W and all of this is X, well, W is right here. W is a substring of X. And same thing here, 110, we have 110. Cool. So let's start with the idea. How do you want to think here? So I'll grab the first example, 110, and like a bunch of stuff afterwards. Well, let's to make it easier on ourselves, we'll assume that our string starts with a blank. So usually it's not always given to you that your input tape might start with a blank. You might have to do it yourself. For now, just to make it easier, we'll assume that it exists. So you can always go back and hit a blank. Okay, so it's similar as always. Okay, I'm starting with a 1. Well, I'll cross it with an X. What am I going to do? I'm going to have to go and find a similar one, right? So I travel all the way to the other side. I reach the hashtag. I see a 1, cross it. Cool. Then I'll have to go all the way back, find here a 1, cross it with an X, go all the way back, cross with an X. Same thing. Now, oh, there's a 0. So we'll cross it with something different. We'll say a Y, then go back, And now this is a y. Now when I go all the way back, I'll notice, oh, it's all x's and y's now, so that must mean that my string exists, right? So if we're thinking of a high-level description, we might do something like, oh, if there's a 1 or a 0, so say if 1, cross with x, and then find 1 on the other side. Now, I'm talking very general. It's a bit more than that, as you might have seen. So on the other side of the hashtag, other side. Okay. And same thing if it's like a 0, right? So if it's a 0, we cross it with a y, and then we try to find also a 0. Now, with this first example, if it works from the very first try, then great, we're able to find it. But what if it doesn't? So let's see the other example. 110 hashtag 1110 and then some other stuff. Okay, well, using the same logic, assuming here we're starting with a blank. Well, I have a 1 here, so I'll cross it with an x, go all the way to the other side, x, right? Like there's no reason to do not do this, because this is how we did with the first try. Go back, this is an x, on the other side, x. Now when this is a 0, we'll put a y. I go on the other side, I try to find a 0, but I can't. There's a 1 instead of a 0. Well, what should I do? That doesn't mean that the substring doesn't exist, because you can see it's right here, it's 110. Well, it just means it doesn't start from here, the substring. So we're going to have to do something like reverting everything we've been doing before. So when I go now backwards, okay, I'll turn this x, say, back to a 1, this x back to a 1, kind of like I'm restoring, right? This is back to a 0, back to a 1, back to a 1, and I'll try again. But what's the problem with this idea? When I try again, where I'll make, okay, this one is an x, and I'm going to go the other side, I don't really want to start from here, right? I should want to start from the other side, because this place didn't work before. So, for the very first time, we'll just, instead of marking this with an x, would have marked it with a z. What I'm trying to say, the very first element you're trying to cross from the left-hand side, on the right-hand side, when you find it, you'll cross it with a z. Okay? Just so in case it doesn't work, and when you're reverting, you revert everything other than that z. The others will still be x's and y's, so you can revert them back. But like the z, when you're going backwards, you don't change it. It stays a z. Okay? So I'll leave that to you to type out here, but you kind of get the idea. If it's the first time, we'll use z. But everything I'm explaining, you can write it in a high-level description yourself. Here, I care about more maybe actually drawing it. But maybe let's do one more example before we move forward. Or you know what, let's do part 2, which is like the first time, and then we'll go backwards. So the first time, and again, remember that we're assuming that we're starting with a blank. So 110 hashtag 110. So this should work right away. So the first time, if I read a 1, okay, put here an x and move to the right. So first time we're saying this is an x. Now I have to go all the way to the right and find my hashtag. Well, to do that, if there's an x, or if there's a 1, move to the right. Don't want to overwrite it, I'll fix that in a second. If there's a 1 or a 0, just keep moving to the right. What do you think we should do next? Well, once I find the hashtag, that means I'm on the other side. So read the hashtag, go to the right. Now over here, assuming it's working fine, like I'm looking for a 1 and I find a 1, oh, I'll just put a z here as we agreed. The first time it's going to be a z. go to the, should I go to the right or should I go to the left? Doesn't matter, because now we're going to go into what? To the rewind state, right? Because we were able to find what we wanted to find, we now should just go all the way backwards. If you've seen the ways I've solved this before, usually it's safer to do left. Sometimes it doesn't matter, but like when you rewind, you're going to go to the left anyway, so why not just do a jump start? Remember, by the way, when there's a 0 here that we might read. So we'll take care of that in a second. But like, what if you read a 0? What should you do? If you're looking for a 1 and you read a 1, great. Let's take care of the other possibility. There's a 0, we replace it with a y, go to the right. Just like above, we're going to skip everything. If there's a 1, move. There's a 0, move. Till we reach the other side. And then if there's the 0 that I'm looking for, great. Replace it with a z. Again, because this is like really the first time. And then I'm going to also want to rewind, so no need to make a new rewind state. I'll just go to this old one. So just to let you know what we've done so far, I crossed this with an X, I went to the other side. The first one that I found, I crossed it with a Z. Okay, great. Now I'm at the rewind state, so currently, no matter what you read, you want to go all the way backwards. So say we read a hashtag, go to the left. If there's a Z, we might see a Z somewhere, go to the left. Really, anything, just keep going to the left. 0, 1. Okay, even if there's an X, and if there's a Y, you go all the way to the left, because we're assuming it for this problem. It's given that we're going to be reading a blank. So once I read the blank, I'll go to the right. But when I read the blank, where should I go to? So currently I went all the way back, I'm at the blank, and I moved to the right. So I'm currently here. What should I do? Well, to make it easier on yourself, or like a hint, I'm going to go to a new state. I don't want to go back to this state. I don't want to do that. I'm going to go to a new state. That's essentially going to do the same thing as above. But instead, remember, above was its purpose. It's really the first time I want to cross with a Z. The next times, I'm just going to cross with X's and Y's. So, right here, I'll skip all the X's and Y's that might have been probably there from the other run, right? Because remember, currently I'm right here. There might have been X's and Y's from other runs. So I'll skip those. And then it's literally the same thing. Well, what's the next thing I'm trying to find? Is it a 1 or is it an X? So if it's a 1, cross with an X, go to the right. Notice how like the left-hand side, you're always crossing with X's and Y's. It's only the right-hand side the very first time you want to check. Oh, yeah, before I actually continue with that, we never said where does this 0 go to and where does this 1 go to. We should, so there's also a 1 here, so we should probably mention that, right? So where do you think, if there's a 0 here, if there's a 1 here, what should we do? Reminder, like in the first case, oh, I found a 1, and over here I'm trying to find another 1. Literally the example would be something like this. Imagine you have 110 hashtag and then a bunch of zeros before you find your first one. Well, the first one, there's an X here. I go to the other side, I'm trying to find a 1. If I don't find a 1, it doesn't mean I have to go backwards. I'm still trying to find the first one. So this, I could cross it with a Z because I'm never gonna restore it. It's simply my substring doesn't start from here. So I can replace all of these. And when I find the first one that I'm looking for, I'll replace that one with a Z. And I move forward. So here, if there's a 0, just write a Z instead and go to the right. Go backwards, and same thing here. A Z, and keep going, right? Because it's the first time you're trying to look for something, it's not there, so yeah. That's what we do. Let me remove this so it doesn't look like the 0 is like its own small state. Okay. Maybe same thing for the 1. So okay, so now that so now that we're done with the Z, what should we do in the new state? Okay, so back over here. Say again, I'll focus on the 1. Now I crossed it, I'll skip all the 1s and 0s, and like a hint, it's really the same thing as above, right? Like, oh, there's a 1, we crossed it with an X. Now what? Same thing, I'm gonna skip the 0s and 1s, read the hashtag, then try to find a 1 on the other side. It's literally the same thing as above, of course, almost the same thing as above. Oh, there's a hashtag, go to the right, and over here, if there's a Z from some other run, we'll skip it. If there's an X, skip it. And if there's a Y, also skip it, because there might be these from a previous crossing. Okay. Let me put that over here so it doesn't look like it's on the transition of the other one. Okay, so remember that we're trying to find a 1 in this case. So say I find a 1, I'll cross it with an X this time, not with a Z. Just the very first time we'll cross it with a Z. The next times it might not be the substring, so we'd like to restore them. Remember, like if I didn't really explain it enough, the Z is really the marker where you're checking if your substring might start here. So right now we're checking if my substring starts from here. It might not. In this example, obviously it will be, but like in the previous example, with this one, we started checking from here. If it starts, it turns out it actually starts from here, the 110. Okay, so like here we marked with the Z, we're checking if it starts from here. It might not necessarily start. Okay, now actually where should we go after we cross this one? So I'll cross it with an X and go to the left. Where should I go to? So currently I went to the other side and I crossed it with a blank, or sorry, with an X. Well, I want to go now the same thing as before. I want to rewind all the way to the beginning and find the next element I'm looking for. So, and no need really to make another rewind state. I could just go to the one we already made here, right? Think about it for a second. We're just rewinding, so I could go all the way backwards. Now here, so we're going to be asking the same question, like if I read a 0 instead, what should I do? But first, let's take care of the 0 case where I'm looking for a 0. So if there's a 1 or if there's a 0, keep moving to the right. Finally, we read the hashtag. Now, same thing as before. If there's something like a Y, a Z, an X, just keep going to the right. Skip all those. Until we finally find our 0, so we'll mark it with a Y, not an X, and then we'll move to the left and go to the rewind. So also going all the way back here. So if we keep going with this example, so I went back, I found a 0, other side, oh, there's a 0. Now I rewinded all the way to the beginning. Let's go with this example that works. So maybe a quick question we could solve here. When should I accept? Well, when I rewind, if it's all X's and Y's, I should accept, right? And where am I checking if it's all X's and Y's? Here. So if I'm reading all X's and all Y's and I hit the hashtag here, that must mean I crossed everything that I was looking for. So I must accept. Q, accept. We just terminate. We accept and we stop. But we're not done yet. Of course, there are still some cases. Essentially, these two. So we said when I read a 0 here and when I read a 1 here, where should I go to? Similar to the above, right? Above but before above, when it was 0s or 1s, we skipped them because it was like the first time we're looking. Here, it's more of the example, again, this one. So let's rewrite it. 110 hashtag 1110. So X, z, since it's the first time, x, x, and then a y here for the 0. We go over here, we don't find a 1, we find a 0. So we're not going to cross this element because it's nothing to cross. Instead, we're going to go back, restore everything other than the z's. So if there's a x here, this is going to be a 1 again. And over on the other side, the y's will be 0s and the x's will be 1s. So you see what we're trying to do here. So we're actually going to be using a state. We'll give it a cool name, which is restore. We haven't used this before. So if I can fit it in, I'll name this It's not going to fit. And restore, really like the name. We're just going to be everything other than the z, we're going to be switching back. Okay. So if there's a x, turn it into a 1, go to the left. If there's a y, turn it to a 0, go to the left. If there's a z, don't mind it. If there's a 1, don't mind it. A 0, don't mind it. Really, anything else, we don't care. We're just going to want to go all the way back. If there's something that I missed, maybe a hashtag, go to the left. XYZ 10 hashtag, I think. That should be everything. Okay. Until finally I read the blank. Now, if I read the blank, what do you think we should go to? There's really only two options, right? Like if I read a blank, two options. I either want to go here or over here. Which one do you think? Well, it should be the one above, right? It's not going to be the one below, because the purpose of the one below, the whole purpose of the machine below, which is kind of like a replica of the one above, like the lower half is a replica of the first half. The difference is the first half, the first time we're marking where we're starting to look for our string with the z. The one below, we're not marking with a z, we're just marking with an x, because hey, now we're trying to look for the substring, if it's there or not. So when you restore, that means what you were trying to find didn't work, so you restored everything. Now you're going to try all over again. So you're going to be looking for a new z, a new place to start. So let me give you an example about this. It's actually literally this one, right? So the one that we had. So the first z didn't work, so you restored everything. Now the next time, this is going to be an x. Go to the other side. This new one is going to be your new z, where you're looking for your new substring. Okay? And the old one, the one before it, is still going to stay as z. And now you're looking at a new substring. Okay. Is this everything that we have? Is there something missing? So maybe here you can think about this yourself. So here, when we were skipping zeros, we might need to skip z's, because this might not be your first time looking where your substring should start. So if there's a z, we might want to skip them. Okay, I think that's mainly it. I hope I didn't miss anything, but the takeaway is, I know this might look like a complicated machine, but if you really break it down, like, it's only like the first half that's it's the first half, and then you like copying and pasting it below and making adjustments. Like maybe, okay, the restore state, that's an idea that needs wrapping our head around a bit. But yeah. So maybe this is something cool, that it's not only always checking for something like bn, and bn, just like formats. We could actually do some things like substring, some cool stuff. We could even add binary numbers. You could do a lot more complicated things with Turing machines, because remember, they're computers, right? Whatever you can do with a computer, you can do with a Turing machine. But now we're going to be moving on to decidability. So what is decidability? We want to prove these languages are decidable, and usually there's two ways to do this. Either you try to prove it, you're like literally make a proof for it, or you could use something that you already know is decidable. So usually it's like standing on the shoulders of giants. So For example, we've used these machines before, like EQDFA, which is a machine that you give two DFAs. It'll tell you yes if they have the same language, and no otherwise. So if I give it DFA A and DFA B, it'll say yes if the language of A is the same as B, no otherwise. And of course, then we have EDFA, which you give it a single DFA, it'll tell it if yes if the language is empty or not, etc. There's a bunch of things we've been using. So let's read the first one. A is a language where R is a regular expression describing the language containing at least one string W that has 111 as a substring. So if W is made up of, for example, for this, like some X, some Y, and like they could be any strings, and like there's a 111 between them. So that would mean W has 111 as a substring. So how can we prove that this is decidable? Very important that we understand what the question is really asking, because I think there was confusion when we solved this in class. So if A is decidable, that would mean there's some machine, say R, that decides it. And this R is going to take what as input? A regular expression. Okay, so maybe I should name it something other than R. So we'll call it D. It's taking some rejects R, and it'll say yes if there is some W that belongs to this language, to this regular expression, such that W has 111 as a substring. So X 111 Y. Okay, so we broke down W into X 111 Y. And now, very important, this isn't saying that R accepts everything that has 111 as a substring. It's just saying, oh, it at least accepts one string that has 111 as a substring. Okay, well, what can we compare it with? Of course, you can pause and try to think about this yourself. So the way we could solve this is, well, how about we compare it, or we use the language that does accept everything, every 111 substring. So what I'm trying to say is, say let L. Do I want to say let L? No. How about this? We might not need to construct, but I'll say construct anyway. So construct, let me type it out. Okay. Okay, so one. Construct. What do you want to name it? A DFA A such that the language of A is all strings that have 111 as a substring. So the language of A could be something like sigma star 111 sigma star, such that like sigma is your alphabet and everything. So like this E, assume it's sigma. Then what? Construct DFA B such that the language of B is the language of A intersection with the language of R. Do you see what I'm going with? Like we've done this before. So A could be something like this. A could be like, I'm gonna do an NFA, but you could do this as a DFA after converting. So you read a 1, you read a 1, and then you read a 1, and at the end you accept, and like at the beginning you say sigma, like whatever sigma is, not epsilon, sigma, so like the elements E1, whatever they are, till En, and same thing here. So you're at least making sure that 111 is a substring. So A could be something like that, and B is the intersection of A with R. So now what do you want to check? What do you want to use? Why did I use intersection? Because I don't want to use EQDFA. If I use EQDFA and I like give it A, which is the one that we made, and I give it R, like I make a DFA, which is just the language R, they don't necessarily need to be equal, because again, R doesn't necessarily need to accept every string that has 111 as a substring. It just needs to accept one. So finally we'll say run Turing Machine M on input B such that M decides EDFA. So somebody asked me about this. EDFA is a language that we know is decidable, and I'm saying let M be some Turing machine that decides it, meaning M, if you give it some DFA, it'll be able to tell you if that language is empty or not. So if M accepts, this means B, the language of B, is empty, meaning R doesn't have any string with 111 as a substring. Does that make sense? Because there's nothing, B is empty, that means the intersection is empty. So there's nothing in common between A, which accepts any string that has 111 as a substring, and R. So that must mean R doesn't accept any string that has 111 as a substring. So we should reject, because the machine will say yes if it does have something. If M rejects, that means language is not empty. Like I'll write this like language of A intersection language of R. It's not empty. So we do have something in common. We'll just accept. Okay, hopefully that made sense. And remember, like this machine, what is it taking? It's taking as input only one thing, which is the R rejects, and we're doing something inside. And yeah, and the reason I said we might not need to do the construction for DFAA, because we could have just said, oh, we'll make some DFAB that's the intersection of R and some other language, so maybe some other rejects. That's simply this thing. Like you could construct the DFA from the intersection of two rejects. But I wouldn't have needed to construct DFAA if I wanted to use something like EQDFA, because it would have needed two DFAs. And at the end, we either say yes, so like this thing is being plugged into the no or reject, and this thing is being plugged into the yes or the accept. Cool. And like imagine inside you used some machine, if I can find my cursor, M, that checks if we called it B is empty or not. Okay, so like we use this machine inside our big machine. Great. Let's now do the other one. This took a bit long. So the other part. S is a language that takes as in, or will accept DFA's M if M accepts the reverse of W when M accepts W. So again, as this is a language, it will accept the machine's M, the DFA's M, if when this M accepts W reverse, or when it accepts W, it will also accept the reverse of it. Now, I made a mistake in class where I just assumed that, oh, they probably mean the language of palindromes, right? Because the language of palindromes would mean something like, oh, W is like kind of like the reverse of W, right? That's the language of palindromes. But again, we need to be careful. That's not what they're saying. They're not saying that the DFA-M accepts W when it equals the reverse. All they're saying is, oh, when M accepts W, it'll also accept the reverse of W. So if M accepts, for example, 110, when M accepts 0, 1, 1. That's all they're saying. Like if you it'll accept 1, 1, 0 when it accepts 0, 0, 1. Now, obviously, because of this, probably it means it will also accept the language of palindromes, but not necessarily means it's only that. It could be more than that. So how could we do this? Well, hint, if you want to think about this, a hint, we want to use this time EQDFA. So think how we could use that one. Okay, so the idea is this. The first machine M, leave it as it is. So we're given M, right? If it's given some W, it'll say yes if W belongs to. Oh, this is the machine M. If say W belongs to the language I have. So read that for a second. So you have the machine M, and say you give it W to say yes if W belongs to the language that defines this machine. Now, how are we going to accept the reverse of W? Well, some of you said you want to feed W reverse to something else, which there's an idea there, but how about this? Instead of reversing W, let's just reverse the M machine. So what's the M machine really? It has some start state. It has transitions. And at some point it has a bunch of accept states. Right? How can you really do the reverse of a machine? Well, first of all, this we've done this before. The start state was going to be now the accepting state. And we'll flip all the transitions. So everything is now flipped. And the old accept states will now not be non-accepting. But we can't have multiple start states, so we'll join them all with an epsilon transition from a new start state. Okay, so this was your old start. We now have here a new start. We'll repeat that one more time in case it didn't click right away. Okay, so first of all, let me explain why does it accept W reverse, and then we'll re-say the construction. So, say the original machine, like it read 1 here, then it read another 1 along the way, then it read 0, so you accepted it. Okay? When we reverse it, what does the other machine say? Now it's reading from the old accept, it's reading a 0. Yeah, no, we're still feeding it the same. We're still feeding it the same W. Okay, remember, we're still feeding it the same W. So from the old state, we have a 1. Then we have some other state where it reads a 1 until we finally reach the start state with a 0. Okay. Why does this work? Well, in the old method, we went from left to right with 1, 1, 0. Here we're kind of going the reverse from right to left with 1, 1, 0, 2. But if you accept 1, 1, 0 in this scenario, that must have meant in the original scenario, you accepted 1, 1, 0. Are you able to see it? Like you don't flip the string, because if you flip the string 2, then you're gonna go 0, 1, 1, which is like the same route you took above. No, you do the reverse of the transitions and all that, but you don't flip the actual string. So now when do we accept? So like we're building these in our big machine. Actually, before that, so when does the other machine, I'll call it maybe M reverse, accept? It says yes if W belongs to the M reverse, which means, this is what like I'm trying to say, which means that the reverse of W belongs to M. This is what I'm trying to say. If you feed W to the reverse of the machine, that's as if you're feeding the reverse of W to the machine. So all of this, put it in here. Now we're getting W. We're splitting it into two. Into the machine, like feed W in the first one, then feed W into the other one. And when do you accept? Well, you're only going to accept when, if both of them say yes. So if this says yes, and then you check if this also says yes, then you will say yes too. If at least one of them says no, you'll say no as well. So again, you'll only accept if both accept, but if at least one says no, you'll say no, because you're only gonna, M only accepts W if it also accepts the reverse of W. Okay, now a good question might be, why don't I just reverse W? Like, why don't I just like copy M twice and feed W to it and then feed the reverse of W, which is a good argument. I'm not sure really why we can't do that. Like there might be a reason for that. The first thing that comes into my mind, like what if like W is infinitely long, right? You can't really flip infinitely long strings. They just keep going on and on and on. Like if it doesn't have an end, how can you really flip it? I'm not sure if that's like enough an explanation, but I'll think of something. I'll try to find a reason why we really need to flip the machine M and not flip the reverse of W. Okay, let me just rewrite how we constructed M here, or M reverse. So construct, there's a lot of points, right? I'm just working on the point of M. So construct M reverse, which is essentially wonder if probably there's a shortcut to do that. Whoops. Okay, so M reverse, which is or by need to learn that shortcut. By doing the following steps. So 1, reverse the transitions, or maybe make the old start state accepting, reverse the transitions, make the old accepting states non-accepting, and join, or make them non-accepting, make one, or make a new start state that goes on epsilon transitions to the old accepting states, which we made them, they're no longer accepting. So that's what we want to do here. Is there anything we have missing? Okay. Okay, so let's do this one more time. Make the old start state accepting state, reverse the transitions, make the old accepting states non-accepting, yada yada. Now you might tell me because of the epsilons here, it's no longer a DFA. It's no longer a DFA, so you could just switch it to an NFA. Why am I saying this? Because I don't think we really ever, we never really We never really checked for EQDFA. Do I need that? So I could actually use. I'm pretty sure there's a language that checks if your DFA accepts some W. So we could use that. Now, if we do want to use EQDFA, so I think this is what we did in class. I'm just trying to think right now if it's correct or not. If I feed this M and I feed this M reverse, does it work? I think yeah, this might also work. Because whatever string that M accepts, M reverse should also accept it. That's how you know that you accept the reverse. So yeah, you could use EQDFA. It should be fine here. So two ways you could do this. Either, as we said before, you plug in the two yeses together. But how can you plug in the two yeses? There's probably some decidable language that checks if some DFA accepts a specific string. So you could do that. Or you could use EQDFA. So instead of like checking the yeses, you just plug in M right here and M reverse. And if this says yes, you say yes. If it says no, you say no. So again, there's lots of ways to solve these. I'll leave you to figure out these tiny details. Now, we're not going to be solving this one. So now we're starting actually with decidable problems. And we're not going to be solving this part, because we did something very similar with ABB. So I'll leave it to you to revise that question and then maybe try to attempt to solve this problem. What is this problem saying? Never mind. We are going to solve this problem because I confused it with the next problem. We are going to be solving this problem. Undecidable problem. So ATM, it's the language that accepts MW, so a couple. So the input is actually two elements, M and W. It'll say yes if M accepts the string W. Now we're working with Turing machines, not like DFAs before. So be careful here. When the input is M, it's not a DFA, it's actually a Turing machine, which makes it different. So M on W, it says yes if M accepts W. Prove that ATM is undecidable. We've done this before. ATM is undecidable. So with undecidability, there's three ways or three ideas we've covered, like using the idea of a paradox, or using contradiction, or using reducibility, even though reducibility has to do with all of the above. But let's go over the idea before. So usually with the idea of paradox, with these maybe basic, let's call them ideas that we've seen, like ATM or whole TM, what do we do? Suppose that it is decided by some TMH. So just like I drew before, MW, it gets taken in by H. H will say yes if MW belongs to the couple or belongs to the language, so M accepts W and no otherwise. Then what do we do? Usually, now that this machine exists, H exists, we'll use it to build a bigger machine. We call it D, and like we draw all over H. D usually takes in one input, but that input, like we split it twice into H, because remember, H is going to be taking two inputs. So like the M machine and M again. And we flip the transitions. Why? By construction, because we want to reach some contradiction. So when H says yes, we'll say no, like D will say no. And when H says no, D will say yes. And then we come to the question, which is what happens when we run D on itself as input. And this is the contradiction part. Like we're asking, okay, this is the machine D we created. What happens when it takes itself as input? In other words, what will H say when D takes itself as input? Do you see it? It's literally what's happening on the outside. You have D that you created, and it's taking itself as input. And that's literally what you're asking H. We're asking H, what will D do when it takes itself as input? Like, will M accept W? Will D accept D? Or will it reject it? Well, two scenarios. If H says yes, it will accept. D actually rejects itself. Okay, so H is saying yes, D will accept D, but what's happening? You're taking D as input, and it's being rejected. So that didn't work. What about the other scenario? If H says no, D won't accept D, well, D does accept it. And that's the whole idea of the paradox. No matter how H tries to predict the outcome, it's always wrong. And remember, H is a machine that we assumed decides ATM. So it should always correctly tell us whether M accepts W or not. In the scenario, M and W just happen to be the same like machine, like D is taking itself as input. So we were able to do a construction that doesn't work, so yeah, it doesn't exist. Now, like for yourself as exercise to really see if you get it, prove that halt TM is undecidable. Again, another basic machine, and we've actually proved these both before using the paradox idea. So just pause here for a second and see where should you plug in halt TM to get the same scenario. What's really different in the proof? So this is going to be the difference. Well, of course, obviously, first, instead of supposing if ATM is decided, we're supposing now halt TM is decided by some machine, and we'll accept if MW belongs to halt or if MW belongs to, doesn't belong to halt. But what does that mean? Before MW belongs to ATM, if M accepts W. In this case, it will belong if M halts on W, like if it stops. Regardless if it's accepting or rejecting, if it stops, it'll accept. Otherwise, it'll reject. And what about here? What should we do for this part? Well, instead of rejecting, we'll just say loop forever. Why? Because again, when we run D on itself, H is supposed to predict correctly if D will halt on D or not. Well, when it says, say, let's do the no part first. Say H predicts that no, D won't halt on itself, will D simply outputs like accepts and like terminates. So it did actually halt, so that prediction was wrong. What about if H says yes, D will halt, it will stop? Well, D actually keeps looping on forever and forever, so it never really stops. So it also predicted it wrong. No matter how it predicts, it's always wrong, and that's really the idea of trying to create it in terms of paradox. Like technically this is also a contradiction, but maybe a different type of contradiction, which will the one that we'll see in a moment. Okay. Show that ATM is Turing recognizable. Well, what's that? This is just a reminder for you that halt TM, it being recognizable, you only care about the accepting part. Why is the ATM Turing recognizable? Because you can make a recognizer for it. It's pretty simple. Just run M on W. If M accepts W, then you'll accept. If it doesn't, then you'll say, like, if it should either, let me repeat this. There are three scenarios. Either it'll say yes, it'll say no, or it might loop forever, right? So all we're saying is run M on W. Run it. If M accepts W, just say yes, you're done, you made a recognizer. If it says no, or if there's a scenario, of course, the scenario it might loop, you don't care about those parts. All you care about is the yes part. That's how you make a recognizer. It's able to recognize. But the no or the looping, that's the job of a decider. If a decider should be able to tell that stuff as well. But with a recognizer, all you care about is the yes part. You could make the no part too, but it won't make a difference. Okay, let's do this one. Okay, given MW, consider the following Turing machine. M1, on input X, if X is not 0, 1, accept. If X is not, or if X is 0, 1, accept. If X is not 0, 1, then simulate M on W, like run it. And if that accepts, then you'll accept. So right off the bat, what are they saying? Always like maybe try to draw to understand what's happening. They're creating a machine M1 that takes as input X. And they're saying if X is 0, 1, you'll accept. If X is not 0, 1, then what do? You run M on W. What's M on W? Well, we'll see in a moment. But if M accepts, you accept. Then you accept as well. So what is the language that accepts M1? Complete the following. So what is the language of M1 that we just created? Two scenarios, either M accepts W or not. And like imagine M and W, they're arbitrary, but like imagine they're fixed for a moment, like it's a single M and a single W. Well, if M accepts W, what does M1 then really accept? If it's 0, 1, it's accepting, but it's running M on W on everything else. Well, if M accepts W, that means you accept everything. You're always accepting 0, 1 no matter what. But anything other than 0, 1, you're running M on W. And remember, they're kind of fixed, like it's a specific M and a specific W. If it's accepting, then it's always going to accept no matter how many times you run it. So like it's everything. However, if M does not accept W, then its language is simply the single element 0, 1. It's like 2 digits or 2 characters, but it's a single element, 0, 1. Okay, part B. Using A or some other method, show that the language M, such that M is a Turing machine and the language of M is singular, is not Turing decidable. So what is singular? It means it only contains a single element. Show that this machine or can't be decidable. It doesn't exist. Why is that the case? By the way, this we've solved this before, where we used to construct machines like M1 ourselves. But like in this question, it's given to you at the beginning as a hint, kind of to help you out with the question. So M1 is taken as an input X. If X is 0, 1, it'll accept. Otherwise, you run M and W, and if M accepts, you accept. Just for fun, say that this language is decidable, as always, like this one here. Call it L. Assume it is decidable. What does that mean? And like R decides it. Well, if I feed R any machine M, what can R tell me? Reread what L does. So if you have R, you give it some machine. I'll call it X, so just so you don't get confused by the letters. Assume X is any Turing machine. But there's an X above there as well. I'll call it Y. It doesn't matter really what letter you give it, but I don't want you to be confused with other things. So R is taking Y as input. It'll say yes if the size of the language of Y is singular, so 1. No otherwise. That's what R does. And they're trying to tell you to prove that R doesn't exist. So this actually isn't possible. Why? Well, just look at M1, the way we constructed it. What would happen if we run R on M1? Like imagine you constructed all these machines and you simply run R on M1. If R accepts, what does that mean? It means the language of M1 is singular. But when is it singular? Go back to part A. It's singular if M does not accept W, right? Because for everything other than 0, 1, you're running M on W. So if the language turned out to be singular, that must mean M does not accept W. Not accept W. What about if R rejects? So language. We technically know that it's everything, but all the machine tells us is that it's not 1. But if it's not 1, it must be everything. Like these are the only 2 scenarios for the language of M1. It's either a single element or it's nothing. So that means if it's either a single element or everything, not nothing. So that must mean that the other scenario happens where M accepts W. Do you feel this is okay or this is a problem? This is a problem because what machine if you assume that L is regular exists, you essentially just made a machine, say call it D, that decides ATM, which we just proved a second ago is not decidable. Why? You're given ATM, say D is given M and W. At some point, you're able to tell if M accepts W or not. So you're able to say here, for example, you say you reject for D, and here you can say accept for D. So D decides ATM. Why? Because it's correctly able to tell you whether M accepts W or not. And why did this happen? Because of our original assumption here that the language assumed that it's decidable. So that must mean original assumption is wrong. It's not decidable. So like at the end we can say here contradiction. Like I never really write this. I just assume that you guys know it, but obviously we should write it. That contradiction, we called it L, so it's not decidable. Since if it was, we would have reached that ATM is decidable, but we know that ATM is not decidable. Okay, hopefully that one made some sense. And this is a recurring idea. We've solved this before. So this next part, I'll leave it to you to try out on your own. So this is the question that I got confused with before. So A epsilon TM, you can see why I got confused. It's similar to ATM. So A epsilon TM is the machine. It's the language. It'll accept M if M is a Turing machine that accepts epsilon. This is not decidable. Even this thing, like you can't make a machine that will tell you if another Turing machine accepts epsilon or not. I know it sounds simple, like why not just run that machine on epsilon? Well, you don't know if that's the whole problem. You can't simply run it because what if it loops forever? So I'll leave you to try to solve this. It's a similar idea to before. You might create a machine M1 that looks like this. And we actually did solve a very similar question with ABB. What is AAB? It's the language, very similar to this one, but instead of epsilon, we're saying, oh, it accepts ABB instead of epsilon. Same idea, right? Like you're specifying some string you're going to accept, whether it's epsilon, whether it's ABB or XYZ. It can't work. Why? Well, try to solve it, and maybe you can check the previous recording where we did this one. Like this was one of the earliest ones where we first started with undecidable problems. Leave that to you, very similar to this one, and of course to this one here too. But maybe this one is a bit more neat because they kind of help you out with creating the machine M1 before you do the decidability or the undecidability. Okay. Now, we come to the third type of problems we've worked with, which is the reducibility. So undecidable problems here with reducibility. Well, let's do these. Now we already solved 5.22 last time, so maybe right now we'll focus on 5.23, but it's a similar vibe to the one previous. So show that A is decidable if and only if A is mapping reducible to 0 star 1 star. What does that mean? Well, let's just do this one. So when is it decidable? Well, let's prove both directions. They're saying if and only if, right? So like we can prove one direction and the other one. Which one do you think is easier? Like left to right or right to left, as I check my notes so I can remember. And I can't find it. Let's just say, okay, so if we assume that A is decidable, can we get that A is mapping? Okay, I think the other direction might be easier. Why? Because you're given that A is mapping reducible to 0 star 1 star. Why? So now you're given this and you want to prove, so required to prove that A is decidable. But there's a theorem that tells you if you have A mapping reducible to something like, call it B. If you have A reducible to B and you know that B is decidable, then that must mean that A is decidable. Well, is B decidable? Yeah, B is regular. It's a regular language, so obviously it's decidable. So we can conclude that A is decidable. Why? A is reducible to B. B is some language that's decidable, so A is decidable. Why is B decidable? Well, it's regular, so it's definitely decidable. So that's one direction. The other way, which is a bit harder, A is decidable. That's what's given. want to build a mapping. Want to build now the actual map that takes us from A to 0 star, 1 star. Now, why is this part harder? Not really harder, just like it's unfamiliar. We haven't solved maybe a lot of questions from this format, but this is essentially what we want to do. Assume you're going from one set to the other using some mapping F. And in this original set, there's a lot of elements. There are elements that belong to A and that don't belong to A. So say W belongs to A, and W doesn't belong to A. The ones that do belong to A, and there are many, we're gonna map all of them to something using the mapping W. So here it was W, now here it's gonna become f of W. That belongs to the language on the right, which is B. I'll just call it, which is like 1 star, 0 star, 1 star. That's what it means to be mapping reducible. You're able to map the W's that belong to A, and on the other side, they're also going to belong to the other language. And then the ones that don't belong, like here, W doesn't belong to A, they'll be mapped to something or multiple things that don't belong to the other side. Well, simply, what's something that belongs to the other side? I could here say 0, 1. And for here, I could say 1, 0. So what am I saying? I'm creating a mapping, I'll call it f of W, such that they're getting mapped to 0, 1 if X or if W used to belong to A, and 1, 0 if W didn't belong to A. I'm free to do that. I made the mapping. Does this part make sense? Like, I'm just mapping the things that used to belong to A to 0, 1, which belongs to B. And if they don't belong to A, I'm mapping them to 1, 0. There's nobody that's stopping me from doing this. I'm free to do this mapping. It exists. However, this mapping has to be mapping reducible, or mapping reducible. It has to be computable. Is it computable? So we have to first, we need to prove two things. We need to prove that if W belongs to A, if and only if, or that's equivalent, same thing, to meaning that f of W belongs to 0 star, 1 star. Did we do this? Yes, by construction we did this. When something belongs to A, it belongs to 0 star, 1 star, and when it doesn't, it doesn't belong to the other side either. So that's the first thing we did, it's done. But is this mapping computable? Computable means, is there some Turing machine? Is there some Turing machine that can do this mapping? Like, is there some Turing machine? You give it W as input, like on the tape. And when it's done, you get f of W on the tape. So say something very similar. So we don't know what W is. But if W was like 0, 1, 0, 1, and like f of W just flips the zeros to Y's and the 1s to X's. This is what we're trying to say. Is there a mapping that can do that? Not this specific thing, but whatever A is. Y, X. Is there something that can do that? Like, is F computable? Yes, it is computable. Why? Well, since A, we're given that A is decidable. That's all we need. If A is decidable, that means there's some machine that decides it. So there's some machine. You give it W, it'll tell you yes if W belongs to A, which is what we, and if it'll tell you no if W doesn't belong to A. That's all we want. That's exactly what we want. But instead of outputting yes right away, what we're doing is, oh, the yes part is what? Remember, like, this is what we mapped it to. Before saying yes, just change the tape to be like all blank, and now just stop it with 0, 1 in this case. And in this case, before like outputting no, erase the tape and just write 1, 0. That's it. Remember, we're starting with a tape W, when we stop, if W does belong to A, we want it to write 0, 1, and if it doesn't belong to A, we want it to write 1, 0. That's how we constructed it, right? I could have put it in here anything other than 1, 0, as long as it doesn't belong to 0 star 1 star. I obviously picked 1, 0 because it's like the reverse. It can't belong to 0 star 1 star because the ones come before the zeros. So yeah, that's the other direction done. We first build the mapping, which I'd say is there's no easier part. You just build them, or no easier or no harder part. You just build the mapping and then you have to prove whether it's computable or not. In this case, it's right away computable because we know that A is decidable. Okay. We're left with these couple of questions we didn't have enough time to solve, which is a shame because they're really nice questions. Should we do them here? Obviously, try to solve them yourself and think about them. And I'll try to give you an idea about them. He says as he solves them. So 5.24. Let J be the following: W, and either W belongs equals 0x for some x's in ATM, or W is 1y for some y which is not in ATM. Show that neither J nor J complement is Turing recognizable. So this is a really nice question because usually one might assume that what? If a language is not decidable, then either it or its complement is Turing recognizable. That's what someone might assume. But as you can see here, that's not necessarily the case. They're saying prove that neither J nor its complement is Turing recognizable. What does that mean? Neither J is Turing recognizable nor J is co-Turing recognizable. So languages like this do exist. So how are we going to do that? Well, to prove that, we'll just simply, if you remember, if we can mapping reduce something that we know is not recognizable, like say ATM complement, because I know that ATM is Turing recognizable. If I can reduce ATM complement to J, what does that mean? Is it possible that J is recognizable? No. It's not possible. Why? If I'm able to reduce ATM complement to J, there's no way that J is is recognizable. Why? Assume that it is. If I assume that J is recognizable, since ATM complement is reducible to it, that must mean by the theorem, just like the theorem before that said, oh, if A is reducible to B and B is decidable, then A is decidable. There's also another theorem that says, oh, if A is reducible to B and B is recognizable, then A is recognizable. So it won't be possible here since ATM complement is not Turing recognizable. So we just have to prove this part, the reducibility part. How can you prove that ATM is reducible to J? And obviously, you can think about it, it's going to be the same thing for J complement. We're also going to be reducing ATM complement or some other thing to J complement. So you want to reduce something that you know is not recognizable to them. So how can we reduce ATM? Well, it's right there. It's right there. W belongs to 1y, but W equals 1y for some y belongs to ATM complement. Like it's literally right there. ATM is mapping reducible. So let me write it. ATM is mapping reducible to J by the function that they kind of wrote for us. F of y equals 1y. Again, why is this mapping reducible? Why does it work? Well, what are they saying? If there's some y that belongs to ATM complement, right? Y belongs to ATM complement. They're saying, oh, just add a 1 to it at the beginning You can do that. Like imagine you have a program for something, and you're just adding literally the symbol 1 at the beginning. You could do that. So this is f of w or f of y. So if y belongs to ATM, you're just saying, oh, add a 1 to it, and we know that this equals w, which belongs to j. Can you see it? Literally, all that's happening is you're adding a 1. Why does this now belong to j? Because that's how they created it. W equals 1y for some y is an ATM complement. So for any y that is an ATM complement, if you plug in a 1 at the beginning, you get something that belongs to j. So you're able to mapping reduce. And the other way around, why does that one work? Well, let me maybe put here a question mark, like we're trying to prove it. Is ATM complement mapping reducible to j complement this time? Yeah, it is. Why? Well, let's use the other part. Using the same logic, they're saying W0x belongs for some x in ATM. Well, what does that mean? Same logic. ATM is reducible to j, right? Why? By, let's maybe not name it something else, by g of x equals 0x. Same thing as before with the f of y, but the difference is now you're plugging in a 0 at the beginning of the machine instead of a 1. But if this is reducible to this, then the complement is reducible to the complement. We've done this before. If this is reducible to this, then the complement is reducible to this, and like we're done. So that must mean that j complement is not Turing recognizable. Why? Or not why? Well, why isn't j recognizable when we know that ATM is recognizable? Like ATM here is recognizable, and we reduced it to j. Why doesn't that make j recognizable or j complement? Well, it doesn't work from left to right. It has like the left-hand side isn't what has to be recognizable. It's the right-hand side. So the theorem says that B is the one that needs to be decidable or recognizable. It's the right-hand side of the mapping that needs to be reducible or that needs to be either decidable or recognizable. Why? Because imagine it like you're using the right-hand side to build the machine that's on the left-hand side. So if the one on the right is this is the one that needs to be decidable, because you're saying that A is at most as hard as B. So it's the B that you care about either being decidable or recognizable. So that's the first part, or 5.23. I say the first part because like they're related, kinda. They don't need to be related, but we can relate them. Again, I'll maybe say it real quick. We were able to prove this how we reduced ATM complement to j and we reduced ATM complement to j complement, which makes both of them not Turing recognizable because ATM is not recognizable. Very important. This isn't saying since ATM is not Turing recognizable that J is. That's not how we were using the theorem, because I don't think there's a there might be a theorem that says that. I'm not sure. But what we are actually saying is that assume that J complement is recognizable. Using this theorem, that must mean that ATM is also recognizable, but we know that it's not, and we reach a contradiction. Okay. 5.25. Give an example of an undecidable language where B is reducible to B complement. Right away, when they say this, we have to give an undecidable language, that's fair, where B is reducible to B complement. Why does that work or not work? Well, that's not what I meant to say. What's the hint of my language? Obviously, it's undecidable, but can one of them be recognizable or not? Maybe. Maybe. let's see. Assume we said that B is recognizable, but B complement is not recognizable. I think that would be okay. You might be able to find a language where B is recognizable and B complement is not recognizable, and you're able to reduce it like this. But the other way around, like if you say this is not recognizable and this is recognizable, that won't work, because when you like mapping reduce it, that must you have to conclude that the first one is also not reducible. But I'll make it easier on us. Let's just use J. Like this will work, or this, I'm not sure if it'll work for what we just mentioned down there, but it'll definitely work if for languages that are neither Turing recognizable nor co-Turing recognizable, like how we have J here. So we could actually use J and it'll work. How? Let's first do J complement. Like, what's the opposite of J? Well, it's W where 0x or x not in ATM. Or not in ATM, or like I could say in ATM complement. Like imagine they're saying, oh, if W is 0x and x is in ATM, like if it starts with 0 followed by x, then that must mean it's in ATM. So I'm just saying, oh, well, same scenario. It starts with 0, but it's not in ATM, or starts with 1, and you can kind of guess what I'm going here. Y is in the complement of the complement, which gives me ATM. But that's obviously not everything. There's the scenario where, oh, W could be nothing, or doesn't even begin with 0 or 1. So W doesn't begin with 0 or 1. So that's J complement. It might be more like, of course, there's the scenario where what if x isn't even an ATM? I think it might be handled in this like third and fourth case. Like these two are, I'm grouping them into one, but like they're technically third and fourth case. I'll help you out with something. Yeah, like this is a bit extra. Like this is if somebody really wants to understand the ideas of reducibility. I'll say f of w is the following. So I'll give you the mapping. Maybe you can try on your own to prove it. I'll say 1x if w is 0x, and 0y if w, or yeah, if w is 1y. There might be a third case that we care about. I'll leave it blank for now. But like these are the two main cases. Now, okay. Now, what do we need to prove? So this is my mapping. I kind of need to prove. Now, is it decidable? Or sorry, is this mapping computable? We can right away say sure. Why is this computable? Because really all we're doing is the following. Imagine you have a Turing machine where you're given some x and some y, like they're arbitrary. All you're doing, oh, there's a 0, I'm switching it with a 1. And if there's a 1, I'm switching it with a 0. This is definitely computable because all you're doing, you're leaving the x no matter what they are. No matter what the x and y are, you're leaving them. You're just switching the very start from 0 to 1 and from 1 to 0. So that's easy enough to do. But the harder part to do in this case is the following. How can you prove that w belongs to J if and only if f of w belongs to J complement? How could we do that? Well, break it down into two parts. Maybe do this first part, like if w is in J, does that mean that w or f of w is in J complement, and if w is not in J, does that mean that f of w is not in J complement? Remember, that's the whole point. If it's like if and only if, for the reason this works is, remember the whole drawing, when it does belong, the mapping should also belong, and when it's not, it should not. So here it should, and here when it's not, it should also here be not. So you have to prove these two parts. Again, the decidability or the computability part, that's straightforward. This is the part that we care about. I'll give a big hint, like these x's and y's, they don't literally have to belong to ATM, right? They could be anything. All we're saying is you're given some input that starts with a 0, change that 0 to a 1. You're given some input that starts with a 1, change that input to a 0. I could literally have written here like x and x, and it wouldn't have made a difference. Like all I'm saying, oh, if it starts with 0, make it a 1, and if it starts with 1, make it a 0. That's what really I'm saying. But I left the 0, the x and y, so it's more straightforward to you. Okay, maybe the first part. So when I'm proving 1, so when I'm proving part 1, one of the first things I have to do is what? Well, what if w is 0x? What if w is 0x? What is f of w doing? So remember, this is w that belongs to, this is w equals 0x that belongs to J. Okay, so x belongs to ATM. Then, what is our mapping doing? All our mapping is doing is the following. F of w becomes 1x, right? All we change is that 0 became 1. And what about the x? The x stayed in ATM. Remember, like x here is arbitrary. It could be anything. X stayed in ATM. Whoops. But like now it has a 1 at the start. Does that mean that, can I conclude that f of w belongs to J? Can I conclude to J complement? Can I conclude this? Well, yeah. Oh, what did I write over here? Let me fix this part. It does. Why? Check what the J complement definition is. J complement says, oh, if you're some y in ATM that starts with a 1, I'll accept you. It's literally here, like 1x with x is an ATM. X or y, they're just arbitrary, right? They could be anything. Here we're saying what? I'm saying, oh, the mapping made it 1x and x is an ATM. Does this belong to J complement? Yeah, well, J complement will accept things of the format 1y where y is an ATM. Like just, this is some symbol that I wrote. It could have been x, it could have been a, it could have been anything. All I care about is it's something that belongs to ATM and starts with 1. This is here, over here. X is something that's an ATM and it starts with 1. So yeah, obviously it does belong. So this one, this part worked. Okay, so this part worked. But these aren't all the cases. All right, so for part 1, you have to prove it for all the cases. Well, there are 2 cases for J. Either W starts with 0, 1, or W is 1y with what? Y. So this belongs to J. So Y is in ATM complement. When you do the reducibility part, let me see if I can put this up, or is it too late? Yeah, it's one entity, that's too late. I'll write it up here. So, what does the mapping say? Well, f of w, all we're doing is changing the 1 to a 0, so this becomes 0y with y still in the complement. Do you see this somewhere in J? Do you see something that starts with a 0 and followed by something that's an ATM complement? I see it. It's right here. If I can find my cursor. Something that's starting with a 0 and that something is an ATM complement. It's right here. Something starting with 0, that's something with complement. Remember, x and y, they could be anything. They don't have to be, in this scenario, the mapping doesn't care what x and y are. So they're unchanged. Whether they belong or don't belong to ATM, they are not changed. What is changed is just, oh, it starts with a 0, it became a 1, or it doesn't. So that must mean that f of w belongs to J complement. So actually, this first part is now over. Now, the other part isn't hard. It's similar to it's similar to this, but there is a case where, like, for these two. So when you're doing it, I'll leave it to you. Like, come on, do something yourself. So for this one, when you're doing it for J complement, it's going to be a similar case, but there are 4 cases. You'll do this case, which will look similar to what we did. You'll do this case, which is similar to what we did again. Like, you're just going to be flipping the 1 to a 0, and like, imagine this will become a 1 and something followed, and that something is an ATM, 1 and something, it's followed by ATM, it's right there. So these 2 cases are straightforward. But what about this 4th case? So what if W is epsilon, or W doesn't begin with a 0, 1? So this is the case. If you don't get this case, that's fine. But that's where the mapping comes in. You remember when I left something blank? So this actually has to be something that we have to specify. Remember, if this if W where am I? Oh, if W doesn't belong to J, f of W shouldn't belong to J complement. I'm just trying to. So this 0 is when we have the other cases. Either it's epsilon or doesn't begin with a 0. So not begin the 0 or 1. I'm just trying to remember if Z0, it's some fixed element in one of the sets. I'm just trying to remember if it belongs to J or it doesn't belong to J complement. Okay, I want to say it should. Okay, so remember, this is when we're doing it for part 2. So when W is not in J, meaning it's in J complement, f of W shouldn't be in J complement. So I think Z0 is something fixed in J. Just thinking of it like this. So remember, in the 3rd and 4th case, when you're mapping it, they shouldn't belong to to J complement. So you're choosing something that's not in J. It shouldn't go to J complement. So I'm just something fixed in J rather than J complement. Okay, this question has been going for far too long. The end goal is, I don't expect you to try to solve, I don't expect you to completely get this part or try to do it yourself. So 5.24 and 5.25, maybe 5.24 a bit, it wasn't too bad, right? But 5.25, it's a bit over. The purpose of it wasn't to intimidate you or to scare you or, oh, I don't understand this. It was just try to let you get as many idea of this reducibility as you can. Like, if you follow it, it kind of makes sense, the whole reducibility and the mapping. There's something there. Yeah. So for this part, for like 5.25, at least for 5.25, if you can try to solve or mimic what I did, that's great. Or just maybe re-watch and try to understand as much as you can. And remember, it's not completely done. Like, we did part 1, but we never did part 2, which is similar to part 1 in some cases. So like when W is not in J complement, when W is not in J, you have to prove that the f of W is not in J complement. So, well, if W is not in J, that means W is in J complement. So there are these 4 cases you have to take care of, or maybe like 3 cases, and you have to prove that the mapping doesn't go back to J complement, which is easier said than done. Or maybe it's easier done than said, because it's confusing when I'm talking about it like this. But again, let's just go maybe real quick over everything that we did. So we started with Turing Machine. Okay, drawing this machine. Maybe not, so not too hard here. Remember, like, there's a lot of parts that we reused. So my advice for Turing machines is just try to get a good general high-level description as much as you can. Now, I'm not sure if you're going to need to draw a machine, but the more you're able to describe it, the easier it will be if you need to draw. Decidability, assuming that using that something you already know is decidable to prove what you're trying to prove. That's usually how we go here. Undecidable problems, either the paradox idea, so undecidable problems, either the paradox idea, which is essentially contradiction. Remember what Turing recognizable is. More undecidable problems where we create a machine. Of course, with all of these, we're assuming that they are decidable, and then we reach contradiction. Except maybe for the reducibility, where it's more building the actual proof. Like, I think rarely here we use contradiction, except in these scenarios. Okay, so hopefully that made sense. I know the last part, maybe, I hope you didn't lose maybe confidence in the last question. I maybe should have said beforehand, it's taking it up a notch, right? I like to solve the hard problems, so whenever you're trying to solve, or whenever comes in the exam, it'll look easier for you. Okay, so that was it. That's going to be it for the recitations for this semester. Hopefully you enjoyed, and good luck in your exams. I won't see you in the next one because this was the last one. Goodbye.